Plastics revolutionized our world, but they came with a catch. They don't go away. Especially thermosets, which are tough and durable but once cured can't be reshaped or recycled. What if we had materials with the strength of thermosets, but the reprocessability of thermoplastics? Introducing Vitrimers, a new class of smart polymers that could transform how we think about materials, manufacturing, and recycling. Vitrimers are covalently cross-linked polymer networks like thermosets but with a twist. Their bonds can reversibly rearrange under specific conditions, typically heat. This behavior is enabled by dynamic covalent chemistry, where crosslinks can break and reform without degrading the polymer backbone. One common mechanism is transesterification, where ester bonds rearrange when catalyzed under heat, allowing the network to flow slowly like glass. Let's break down what makes Vitrimers special. Thermal stability like thermosets, reprocessability like thermoplastics, self-healing under heat, recyclable and weldable, even when cross-linked, high mechanical strength, retained over multiple cycles. Their viscosity decreases gradually with temperature, following an Arrhenius-like behavior, instead of the abrupt melting seen in thermoplastics. Vitrimers are already making an impact. Automotive and aerospace, used in lightweight composite panels that can be reshaped, repaired, or recycled. Ideal for reducing waste in high-performance sectors. Electronics, used for stretchable, reworkable circuit substrates, improving device lifespan and recyclability. 3D printing. Printable Vitrimer inks allow objects to be reshaped post-print, enabling dynamic prototyping and repairs. Coatings and adhesives. High-performance industrial adhesives that can be debonded and rebonded using heat. No solvents required. Vitrimers can be synthesized from epoxy, polyester, polyurethane, and even bio-based monomers, by introducing dynamic cross-linking units often via catalysts like zinc acetylacetonate or organic acids. Unlike traditional recycling, Vitrimer processing doesn't require melting just enough heat to activate bond exchange. Research is now focused on bio-based Vitrimer systems from lignin, vanillin, and other renewables, multifunctional Vitrimer composites with embedded conductivity or shape memory, closed-loop manufacturing where end-of-life components can be ground and reprocessed into new parts, but challenges remain, like reaction kinetics control, cost of catalysts, and scale-up for industrial production. Vitrimers bridge the gap between performance and sustainability. They don't just add functionality, they redefine how materials live, evolve, and come back to life. Vitrimers aren't just a material, they're a mindset shift in polymer science.